Hello, good night, my friends. How are you? You see, inside this room it is warm. It is warm and it is good. And today it is Friday. Tomorrow it is Saturday, as you know, and that's good for me because I don't work, and I like to not work. You see. Also, I think that almost all the people does not like to work because the human people, it is a thinker, likes to think, not to work. Human people, it is a little bit lazy, and I think the human people likes to do only the things for passion, but almost the time they don't do that. You see, because they have not that opportunity. So in this video I'm going to test my memory, and I'm going to, let us say that I have a function f of x, which is equals to, let us say, arctangent. You see, arctangent of 1 of x if x is greater than 0, and if x it's equals to 0, let us say it is equals to pi over 2, and if x is lesser than 0, let us say, why not, it is equals to the, for example, x squared plus 1. And let us take another function, this one, h of x equals to the a to the x, the exponential, you see, times f of x. And I want to show, if I take the interval, this interval over here I'm going to write down, the closed interval 0 to 1, so I can say that there is a point, let us say C, which this point, there is a point C which belongs to the open interval 0 to 1, where the derivative of h at C, it's equals to a minus 2 times pi over 4. You see, I'm testing my memory about some exercises I made some, I can say, some years ago. So in this problem, also to make the solution, I'm going to apply to the Lagrange theorem. And so if the function h it is continuous at the closed interval 0 to 1, and also if the function h it is differentiable at the open interval 0 to 1, so I can say that I can apply to the theorem, and I can say that there is a point, let us say C, exists a point, let us say C, which belongs to the open interval 0 to 1, where the derivative of h at C it's equals to a minus 2 times pi over 4. So first of all, I'm going to show to you that the function h it is continuous at the closed interval 0 to 1. As you can see, I have here a product. The exponential is continuous, and the product of the two continuous function, it is a continuous function. I only have problems with the function f. Yes, I have, because if f it is defined at the interval open at 0 and closed at 1, of course I have no problems, because I only have problems if this x over here it is equals to 0, but I am putting off the number 0, okay, off. So if it is off in this interval, the product of a to the x times f of x, it is a continuous function. but I must show that the function it is continuous at the closed interval 0 to 1. So I must study the continuity of this function at the point 0 to the right. Okay, so let us take the limit when x approaches 0 by the right of f, in this case arctangent of 1 of x, and let us say if this limit it is equals to pi over 2. Okay, but if I take this limit when x goes to 0 plus, the arctangent of 1 over x goes to plus infinite. Okay, but one thing I know the graph, you see, of the arctangent, and the graph of the arctangent it is not difficult to make. Here it lies the line y equals to pi over 2, and over here it lies the line equals to minus pi over 2. Here it is the y-axis, let us say like this, and here it is the x-axis. And so the graph it is more or less something like this. So when x goes to plus infinite, the arctangent goes to pi over 2. So over here it is quite easy to understand that this limit it is equals to pi over 2, and of course it is equals to the image of f at the point 0, because the image as the point 0 it is given by the definition of the function over here. You see, when x it is equals to 0, the function takes the value pi over 2. So it is continuous, of course, at the closed interval 0 to 1. In the case of to show to you that this function, let us say h, it is differentiable at the open interval 0 to 1, it is pretty simple to understand that it is not pretty simple, I think, but I'm sorry, but the product of two differential functions, it is another one function which is differentiable. So as the arctangent it is differentiable at the open interval 0 to 1, and the exponential it is all time differentiable, so I have a differentiable function at the interval open interval 0 to 1. So now it is a question, only a question of the calculations, and I can apply it to the Lagrange theorem. So I'm going to show that there is a point C which belongs to the open interval 0 to 1, where the h prime of x it's equals to a minus 2 times pi over 4. So what the Lagrange theorem, I don't know if you know the Lagrange theorem, but if you don't know the Lagrange theorem, you must know the Lagrange theorem. It says that h prime of c it's equals to h at the point 1, you see, minus h at the point a 0 over 1 minus 0. So here I get 1. What is the value of the h at the point 1? At the point 1, as h is a product I have over here, so I will get a, which exponent it is 1, times f of 1, but f of 1 it is the arctangent of 1. The arctangent of 1 it is pi over 4. I'm so sorry if you don't know this, but I want to go to have some rest, so I'm going to write over here pi over 4 minus h at the point 0. H at the point 0 it's equals to a exponent 0, which is 1, times f at the point 0, which is pi over 2. So I get here pi over 2. Now it is a question of making these calculations. So I will get a times pi over 4 minus pi over 2. That, of course, it is 4. And here I will get 2 pi. So now I can give the same denominator. It is 4. And at the numerator I will get a times pi minus 2 pi. So I'm going to put pi in evidence, and I will get a minus 2 over 4. And I think that this is the result, you see. I'm a little bit happy because my memory is good, you see. So my friends, it was only for fun. Have a nice weekend. Bye bye for today.